In this section, we'll talk about the duality theory. One of the most important discoveries in the early development of linear programming was the concept of duality and its many important applications. This discovery revealed that every linear program problem has associated with another linear program problem called a dual. The relationships between the dual problem and the original problem are extremely useful in a variety of ways. One of the key uses of the duality theory lies in the interpretations and implications of sensitivity analysis. Let's look at an example. Suppose a company produces two products, A and B, and the information is in the following table. So we have the products A and B, the materials they consume, and the profits they will make. And the question is, how does the company arrange its productions to make the total profit maximum? So this is the question we saw earlier. We say this is simply a linear program problem where our objective function is to maximize the profit. So 4x1 plus 3x2, where x1, x2 denotes the number of products A and B. And then with some constraints on the materials. So 2x1 plus 3x2 less than or equal to 24, 3x1 plus 2x2 less than or equal to 26. So this is the problem, what we call the primal problem. Now let's consider another problem. Suppose now if the company does not want to arrange the production, but in terms, it would rather sell its materials to a factory. Then how to determine the sale price of each material to make the revenue? Alright, so the materials and the costs are still listed on the table. So in order to set up this linear program problem, again, we think about, first, what are the decision variables? We want to determine the sale price for the materials. We have two types of materials. So we let Y1 and Y2 be the sale price for each material respectively. Next, we want to determine the objective function. The total revenue for the company is 24Y1 plus 26Y2 because 24 and 26 are the amount of the materials. This is also the price the factory needs to pay, which from the factory's point of view should be as small as possible. So on the factory side, the objective function would to minimize the sale price. W equals 24Y1 plus 26Y2. Next, we consider the constraints to this problem. Well, we say the factory would rather to sell these materials. So from the factory's point of view, the sale price should not be less than the profit. Otherwise, the company would rather produce the products themselves rather than selling the materials. So we have the sale price 2Y1 plus 3Y2 should be bigger than the profit of that product 4. And then 3Y1 plus 2Y2 bigger than or equal to 3. So on the other hand, we say the price should not be too high, otherwise the factory will not accept it. So the model would be of the form of minimizing our W 24Y1 plus 26Y2 with all the constraints we mentioned above. So this is from the factory's point of view, we want to minimize the cost. So this problem in contrast with the primal problem is called a dual problem. So we say that the primal problem and dual problem are actually related. In our examples, the primal problem is from the company's point of view. We want to maximize the profit. From the factory's point of view, they want to minimize the cost of the materials. And then we have these two problems. These two problems, if we write them in terms of the coefficient or in terms of the matrix form, we can find out some relations between their coefficients or the coefficient matrices in the dual and the primal problem. From these two expressions, we can actually see that the difference or the importance the essence for the dual problem and the primal problem is that, first, the primal problem is in the maximization form and the dual problem is in the minimization form. Second, the coefficients in the objective function of the primal problem are the right-hand side of the functional constraints in the dual problem. Third, the right-hand sides of the functional constraints in the primal problem are the coefficients in the objective function of the dual problem. Next, the coefficients of a variable in the functional constraints of the primal problem are the coefficients in a functional constraint of the dual problem. So if we compare these two models saw earlier, we see that this is the primal problem from the company's point of view. This is the dual problem from the factory's point of view. We see that the coefficients in the objective function in the primal problem are actually the right side of the constraints for the dual problem. And one is the maximization problem, the other is the minimization problem. And then the right side of the constraints in the primal problem are the coefficients of the variables in the dual problem. And then next we have all these coefficients for each variable in the constraints. Here x1 has variables 1, 0, 3, are the coefficients of the functional constraints in the dual problem, reading by row 1, 0, 3. And then similarly for x2, 0, 2, 2, we have the second constraint with coefficients 0, 2, 2. So if we use the matrix representation for the dual problem and the primal problem, we can also express them in this way. We also have the primal dual table to help us to see the relations between the coefficients and variables and constraints in the dual problem compared with the primal problem. Okay, so next we say that every linear program problem has a dual problem, whether it's in the standard form or not. So far we only discussed if we have the standard form of a linear program problem of a maximization problem with all the constraints less than or equal to, how to find its corresponding dual problem. How about the other forms? As we've seen earlier, we've discussed how to convert a non-standard form of a linear program problem to a standard form. So by this idea, we can first convert any LP problem to a standard form, and then from the standard form, find out its corresponding dual problem. Recall that if we have the non-standard form of the linear program problem, how do we convert it to the standard form? If we have a minimization problem, we simply change it to a maximization of the negative of our objective function. If our constraint is in the bigger than or equal to form, we can simply multiply both sides by a -1 and then change it to a less than or equal to form. Similarly, if we have an equation for the constraint, we can split the equation as two parts. One is less than or equal to, the other is bigger than or equal to, and then multiply a negative of all the variables less than or equal to -b. So this is how we convert the constraints to the standard form of less than or equal to. On the other hand, we say originally we expect all the variables to be non-negative. If there is no restriction on our variables, we can simply split our variable as a difference of two non-negative variables and then put them in, substitute them in our model. So with this idea of converting non-standard form of an LP problem to the standard form, we can find out the relation between the constraints, the variables, between the primal problem or the dual problem. So if the primal problem is in the maximization form and the dual problem is in the minimization form, then each constraint of the primal problem corresponds to a variable in our dual problem. If the constraint is in the bigger than or equal to form, the variable will be less than or equal to 0. If the constraint is in the equal form, then our variable will be unconstrained. If the constraint in the primal problem is the less than or equal to form, the standard form, then our variable in the dual problem will be non-negative. Similarly, for the variables, each variable in our primal problem corresponds to a constraint in our dual problem. If the variable is non-negative, the standard form, then our constraint will be the bigger than or equal to form. If the variable has no restrictions, then our constraint will be the equal form. And then if our variable is negative or 0 in the primal problem, then our constraint will be in the less than or equal to form. Let's look at an example. If we have the primal problem of maximizing a function with all the restrictions, then we can do it correspondingly to find out its dual problem. So the primal problem is a maximization problem, our dual problem is a minimization problem. And then the coefficient of our in the objective function of our dual problem are the right side of our primal problem, 2.7, 6, and 6. And each constraint in our primal problem corresponds to a variable in our dual problem. So the first constraint is less than or equal to, so the corresponding variable y1 bigger than or equal to. Second, an equation, so y2 has no restriction. Third, a bigger than or equal to form, so our corresponding variable in the dual problem is non-positive. Similarly, we say that each variable in our primal problem corresponds to a constraint in our dual problem. If the variable is in the bigger than or equal to form, our dual constraint in the dual problem is also in the bigger than or equal to form. And how about the coefficients? The coefficients are simply the coefficients of x1 reading from the constraints. So the coefficients of x1, 0.3, 0.5, 0.6, and then bigger than or equal to the coefficient in the objective function, negative 0.4. And similarly for x2, bigger than or equal to 0, so the second constraint is also bigger than or equal to. And then the coefficients, 0.1, 0.5, 0.4, bigger than or equal to the coefficient of x2 in the objective function. So this is the general way of how to relate a primal problem and then construct its corresponding dual problem.